So thank you very much, Victor and Anna, for inviting me one more year in this summer school. I'm Anaís Garrell. I'm a lecturer professor here at the UPC. I am the coordinator of the robotics part of the degree of artificial intelligence. And today I will talk to you about the experimentation of human-robot interaction. What does it mean? It means that we have humans and robots, and in some sense, interacting or collaborating between them. And I will show you how you have to measure and extract conclusions from those experimentations. But before we start with my talk, I would like to show you how my research is going on. My main research focuses on social navigation, so how robots should move in a crowded environment or in pedestrian environment. Here, the difference is that we are taking into consideration how humans move. And what we do is imitate how humans move and apply it to robots, because we want robots to be acceptable by other pedestrians, and we also want robots to follow social conventions. Okay, and regarding this social navigation, we make different tasks and we apply this to different tasks. For instance, here you can see a robot that it's accompanying a person or a group of people in this human scenario. Here, the difficulty is that the robot should infer what is the intention of people and has to adapt his intention to its motion. Okay? On the green, here on the bottom of the image, you can see. I will activate my notes. Okay, here, sorry. You can see the inference of the robot and how the robot tries to understand which is the intention of the pedestrians. We have a second part. Okay, here. I'm also working with drones. So instead of having a robot walking on a 2D plane, we're working with a robot that working a 3D space. And here again, what we are trying is to have drones moving close to people and adapting its motion to pedestrians. Here it's even more difficult because people are afraid from drones. So here not only affects the motion of the robot, but also the noise that the robot produces. And regarding also this social navigation, we also work with collaborative tasks between robots and humans. Here, basically, we have a team of a person and a robot. And the goal was to find an object in an unknown area in an urban scenario. So here, the robot has to plan, has to present his plan, also the human, and has to negotiate with the other person. Okay? Here, the communication between the robot and the person was done by this APP mobile application. And here the robot presents its plan, which is which path will follow. And the person also presents his path. Okay? And at the end, they have to agree. And finally, this is the research that I'm doing the last year. As you may see, in all my research, humans are involved. So it's necessary and also mandatory to have robots capable to communicate with humans. When I mean communicate, I mean natural communication. I don't want a screen, a touch screen, or a keyboard that the humans use to communicate with robots. I want natural communication. So here I present you the work. It's called Hand Gesture Incremental Learning for Human-Robot Interaction. The idea comes from communication between humans is done using speech and gestures. Nevertheless, the 70% of the communication is done with gestures. And so we focus our research on those gestures. Okay? Why not speech? Because our main research is on outdoors. So in outdoors, we have a lot of problems of noise, and it's very difficult to understand the people outside. That's why we are focusing nowadays on these gestures. So the idea is to have an incremental learning. We are using incremental deep learning I won't explain it in detail because I know that you have other talks on deep learning. But the idea is that we want to avoid what is called catastrophic forgetting. I mean, every time that we learn a new class in this research is a new gesture, usually these architectures forget what is happening. Okay? So we are avoiding this problem. And what is the idea? The idea is to have a robot and that knows a set of gestures. So using interaction, you tell the robot, okay, I will show you a new gesture. So learn it. You make that gesture, and after that, the robot is capable of understanding the new class and also remember the other classes. So what is the goal? The goal is to implement a machine learning system to incrementally learn to recognize hand gestures. Here I'm showing you some photos where we have this tail robot and I'm performing the different gestures and the robot is capable of detecting. And I have here a video from one of my students where is showing a new gesture. So here you can see Xavier. Xavier is doing a set of gestures and the system is classifying correctly. And after a while, he tells the system, okay, I'm going to show you a new gesture. Okay? And this gesture is called up. And the system starts to capture this gesture. Okay? So after a while, the system learned that gesture and is capable of classify correctly. So here is recording different gestures. And again, once the system already learned that gesture, he is saying, okay, what is that? What does that mean? It means up. And he changes the gesture and is always capable to detect that gesture. Why it's important, this incremental learning? On the one hand, because humans learn using interaction. Okay? We learn using this interaction and using this communication. And on the other hand, if we have robots capable of learning using this interaction, we will have robots capable of adapt depending on the person who's interacting with the robot. For instance, for Xavier, this gesture means up, okay? But maybe for me it means okay. So if the robot knows that I am Anaís and I'm saying that, he will know that it means okay. But on the other side, if Xavier appears on the image and knows that he's Xavier and Xavier is doing this gesture, the robot will know that it means up. Okay? So this is what I'm doing, and on the one hand, I'm doing all these systems and all the frameworks to make robots even more intelligent. But on the other hand, we have to evaluate which is our hypothesis. Okay? Always regarding the interaction part. Okay, I'm not focusing on how do we evaluate our classification systems, for instance, or our social robot navigation. I'm talking about how do we evaluate this interaction. So my talk today will have these three main items. I will start talking about what is human-robot interaction, just a short definition. Then I will present some modalities and resources for social human-robot interaction, and I will finish with the evaluation method and methodologies for this research. So let's start with definition. Basically, this field of study is the systematic study of interaction between humans and robots. This interaction can be found everywhere that we have a robot and a person. We can find this interaction in industry, in urban spaces or public spaces, or even at homes. So every time that we have a kind of interaction, every time that we have robots and humans coexisting in the same space, we have this interaction. And we have three different levels of interaction. The first one is just when humans and robots are coexisting. Here, this pair just share a working time and a workspace, nothing else. But of course, the robot needs to understand that we have a human and what is the human doing. Then we have one more level, which is the human-robot cooperation. Here, they are sharing the working time, the workspace, and the aim. Okay? They share the same purpose. Okay? They want to solve the same task. And finally, we have the human-robot collaboration. But here, they are not only sharing this aim, they are also sharing this contact. So the robot and the person are in close contact. This is called physical human-robot interaction, when robot is touching the person.
Excuse me, Anaís.
Yes?
You have your first question.
Okay.
Can you see it?
Let me change my screen. Yes, when it gets the picture of the gestures, it only shows one side of the hand. For any reason, shouldn't we rotate the hand also? Depending on the gestures, and depending, I will go back and show you the video. The first part of our architecture is extraction of those points, okay? And this is done with something called media pipe, and we are playing with those distances. And depending on the database or what we want, you have to consider rotations. For instance, maybe this gesture is the same as this one, okay? But this gesture is different from that one, okay? I know I'm answering, but depending on the problem that you want to solve, and depending on the characteristics of the gestures, you will consider rotations or not. But we are capable of be invariant from rotations if you want. But in the case it is recognizing it, I need to run here respecting a new gesture. Yes. You mean in the video with the new gesture? You mean here? Text speaks on one side. You mean one side? You mean one hand, or making also this gesture? You mean this one? I don't know if you. Okay. Usually when you say okay, you make this, not this. Okay, that's the nature of the gesture. But depending on that, we take images from different views. I don't know if I'm answering you, Angel. Okay, so, I understand. I thought that put. Okay. Yes, we can use both hands. Yeah, you can use both hands, and I mean, we can learn with the right hand, and after that, we show him the left hand, and the system is capable to understand that it's the same gesture. Okay, thank you for your question. So I shall continue. I will go forward. Okay. So let me show you some examples, because we have in mind like a specific robots and humans interacting, but there are other kinds of interaction. For instance, here I'm showing you a robot that is capable to guide a blind person. Okay, and the communication is using this stick. So if the robot has to avoid an obstacle, he will turn, and the blind person will understand that. And if there's a stairs, for instance, this stick vibrates. So here we are not using verbal cues. We are just using this motion of the robot and the vibration of the stick. Then we have another example from Honda. They built this exoskeleton. They are in contact. So this is a cooperative and a collaborative interaction, and it's a physical human-robot interaction. And here the communication is done by motion. So the robot in that here needs to understand if the person is moving, and if the person starts to run, if the person wants to stop or sit down or lie down. Okay, and this communication is just done by gestures. No verbal cues, not any kind of social cues. And the last one is that the well-known Now Robot. Now Robot is a small humanoid, but it's a sprite used with children with autism. Medical doctors found that this robot creates an engagement with these children, and medical doctors use this robot to communicate with that children. Okay? In all these examples, we have to evaluate how the robot is working. So we need to have quantitative measures like accuracy, percentage of goals achieved. But on the other hand, we have to study how humans perceive this interaction. Okay? That's why I'm focusing today here. So I'm just studying the perspective of the human, not the perspective of the robot. And another kind of robots that are really used in human-robot interaction are the humanoid robots. Here I'm showing you two examples, the iCap from IIT and the Pepper robot was created in Japan. These robots are really used to interact with people. For instance, a Pepper robot on the right side is capable of understanding emotions, and depending on the emotion of the person that is interacting with the robot acts consequently, and he's achieving a lot of growth regarding this interaction between humans and robots. And one thing that is important when we are using robots with humans is the appearance of the robot. That's why Mori in 1970 created and presented this graph. This graph gives us the relationship between how the robot is, the appearance of the robot is close to human's appearance, and the acceptance of that robot. Okay? So he has demonstrated that as the robot is more close to human appearance, this acceptance increases until one point. Then we have a valley here, and all the robots that adhere will not want to be accepted. What happens if the appearance of the robot is not accepted? That interaction will fade. So the appearance of the robot, if you have to interact with humans, it's very, very important. And another important thing here is that depending on the Q2, this graph will change. For instance, here on the right side, you have a Gemini robot. This is a robot that it's used on Japan. This robot is allocated in this area of the graph, but in Europe, these kind of robots are not accepted, so are more or less in this area. So depending on the Q2 that you are working on, the robot's appearance may change. So now that we know what is neural interaction and you saw some examples of that, let's talk about the modalities and resources for this interaction. So here we will talk about the roles of interaction. It means the roles of the human that is interacting with the robot. The key bits to roles, the awareness in neural interaction. I will show you some taxonomy, why it's important to have a taxonomy in neural interaction. And we will finish with a comparison between human interaction and human-computer interaction. Regarding the roles of interaction, we have 5 different roles that the person can adapt when it's interacting with the robot. The first one is the supervisor. That person has to oversee the number of robots that are working in that moment. And he also needs a global picture of all robots and the whole mission. Finally, needs to understand when a robot is having a problem, the seriousness of the problem, and the effect of that mission. And what is the challenge of a supervisor? So how many robots can a supervisor effectively monitor? So depending on the role that the person is adapting to the robot, we will make different studies. The second one is the operator. The operator is a person that needs to have a telepresence to understand where the robot is and what must be done. It can vary from complete teleoperation to giving high-level tasks to specific mission, and needs the awareness of robot health, awareness of environment, and awareness of what robot is doing to support the task of the mission. And here the challenge is to know how to maintain awareness despite communication limitations. So for each one of the roles, the communication will change. Okay? We will create different interface depending on the person that we are interacting with and we are working with. The third one is the teammate. Here, the robot is a member of a team, and teammates can give commands within the scope of the task and the mission. Here, the interactions such as gestures and voices may be helpful and needs to understand any limitations of robot has in capabilities. What it means, we cannot assume that the cognition of the robot and the cognition of the person are on the same level. Okay? So here, usually humans need to adapt to the cognition of the robot. And the challenge here is how can the robot understand the some interaction vocabulary as other team members? Of course not. So we have to look for a strategy that allows the robot to understand the human. Then we have the mechanic and the programmer. He comes into play if the operator cannot resolve an issue and interaction could happen within a task. Here, the point here is that how much self-diagnostic can the robot do? In an ideal world, we have robots that can tell us, okay, I have this problem, I'm run out of battery, or my leader sensor is not working. But it is not happening nowadays. So the mechanic should know what is happening. And finally, we have the bystander. The bystander is the typical non-trained volunteer. Okay? So it has no formal training using robot, but must coexist in environment with the robot. This example that I'm putting you on the right side. These robots are working on the hospitals, taking care of patients here, for instance. So he's the bystander because he has not programmed that robot. He just coexists and interacts with them. So the point here, the challenge here that we have is that how can a bystander form a mental model of what the robot capabilities are? That's why it's very important the appearance of the robot, because if we have a robot that seems very smart and super intelligent, but at the end the robot is stupid, the mental model is not the same. So in that cases, the interaction may fail. Okay, some comments about the chemistry roles. One person might be able to assume a number of roles for a particular robot, excluding the bystander. Okay, the bystander cannot be a person who programmed the robot, for instance. And assuming that we can determine this information or this interaction needs, we have to design a user interface to support a given role and determine whether multiple roles could be supported in one user interface. We don't want 5 different interfaces. What we want is to have the same interface for all the roles. Like here, I'm showing you some examples. For instance, this robot interacts using a touch screen. Here we have a programmer that is touching the hardware of the robot. Or here we have a robot in an industry where the interaction is doing with contact. So the person touches the arm and shows the robot how to act. And just an awareness is it's very frequently used in computer-supported cooperative work. It was created in 1980, and basically the last definition that was presented was by Yuri in 2001, that says that given 2 participants, P1 and P2, who are collaborating via synchronous collaborative application, awareness is an understanding that has P1 from the present identity and activities from P2. We cannot adapt this definition to our human interaction problem, because we can have single humans or a group of humans, we can have one robot or a group of robots, and we have difference of cognition. Okay? That's what I said in the previous slide. Cognition here is crucial, and we cannot assume that robots are capable to do the same things that people do.
Excuse me, Anaís, you have another question.
Okay. I got a question. How did you add vision to the now robot? Did you use growth, and when I was not version of it? For my research work, I'm trying to do it, but I cannot. Okay. I think now it's working on the ROS. I'm not very sure. I know that most robot works on ROS. The point here, as you may know, that in 2 years we have to move from ROS 1 to ROS 2. Okay, so I think it depends on the research center. Here at EDI, we are working with ROS 1. And in my classes of the university, we are also using ROS 1, the last version, which is noetic. But we will have to move to ROS 2. I don't know if I'm answering you, Carla. Okay, thank you. Is ROS 1 and ROS 2 compatible when connecting multiple machines? You cannot use both ROSes in the same machine. I mean, or you are using ROS 1 or you use ROS 2. I think you cannot nowadays to mix different ROS. You can try to bridge them. Yeah, you can bridge them, but I do not recommend it. I mean, I think it's better to have all the machines and all the robots work in the same ROS version. Okay, thank you for the question. So, what is the definition of the human interaction awareness? So here, from the human perspective, is the knowledge that we have of the location, activity, the status, and surrounding of the robot. And from the robot perspective, is the knowledge that it has from the human's command society to direct its activities and the constraints under which it must operate. So as a general framework, we can have N humans, N robots. So the human-robot interaction awareness consists of 5 components: the human-robot awareness, the human-human awareness, the robot-human awareness, the robot-robot awareness, and human's overall mission awareness. The point here is that you cannot assume that robots and humans are in the same level. So until now, you need humans controlling the overall mission. Okay, taxonomy. Why do we need to classify this interaction between humans and robots? Because it's a way to measure properties of systems, and it's easier to compare systems. It's very difficult nowadays. If I'm doing, for instance, social navigation with my robot, and I want to study the acceptance of that robot, and I want to compare my frame with another one, we have different hardwares. It's very difficult to compare them. So if we classify in some terms, if the robots are in the same reef, we can say that we can compare both frameworks. So here, there are many classifications. You can also determine your classification, your taxonomy. You can pick one if you want. I will show you just 2 examples because I have not a lot of time. But for instance, one typical example is comparing the first level is that if the robot is industrial or not industrial robot. If the robot is not industrial, we can classify between assistive robots and non-assistive robots. And inside assistive robots, we have non-social assistive robots and assistive social robots. And here we have the service robots and the companion robots. So if I'm working with a social robot that is capable to navigate, and I know that it's an assistive robot and it's social, so my robot could be made a service robot. So I will compare with other frameworks and other systems that are using robots that are social robots. Here I show you another example. For instance, in the industry, we have that arm robotic. So I can define like how is the communication between the robot and the person. Of course, the communication between the human and the robot don't have to be the same than the robot and the human. For instance, the human uses just acoustically communication, but robot uses acoustically and visual communication. Then, which is the task of the robot, the reliability of the robot, the proximity, if they are touching, if they are approaching, if they're just coexisting, which is the form of interaction between the human and the robot, in that case, collaboration. Okay, so you have to define each level, and with that, it will be easier to compare your works with others. You know that nowadays, if you want to publish and in a conference of the journals, you have to compare, you have to demonstrate that your systems are better than the other ones. So you need to compare. That's why it's so important to have a taxonomy. Okay, and finally, the comparison between human interaction and computer-human interaction. The point here is that human-computer interaction has a lot of years, more than 100 years, but the human interaction has more or less 25 years. It's 25 years old. Okay? So the point is that we cannot transfer all the tools from human-computer interaction into human-robot interaction. So it's a huge mistake to try to use the same theory because you're not taking into consideration all of the stuff that is happening. For instance, we know that robots work in an environment. In those environments, there are a lot of noise. Maybe you have poor visibility. Our sensor always fail. It's something that if you are doing experimentation in real scenarios, you will know that sometimes the leader is not working, the cameras are not working. Then you can repeat the same experiment several times and the robot is not behaving by the same way. And if you have two different robots with the same algorithm, they won't follow the same path. They won't solve the task by the same way. And this is not happening in human-computer interaction. So be careful with that. So let us start now with the main core of my talk. which is these evaluation methods and methodologies for human-robot interaction. So as I said, human-robot interaction is a new field. It has more or less 25 years old. I guess that you know Rashid Alami. Rashid Alami is a professor in robotics, very well known. For me, he's a superstar. And I found him on ICRA, and he told me that everybody's saying that he's doing human-robot interaction, but that's not true. Because having a person and a robot in the same space, that's not doing interaction. Okay? So when we're doing interaction, we have to consider the study of how humans are perceiving that robot. Okay? If you're just ignoring the part of the human, you're not doing interaction. And the point here is that most studies cannot yet be reproduced because we have very different hardware. So more or less, we have to pick some theory from psychologists because it's very difficult here to agree on a methodology on how to carry out the research. Okay? We have not a dictionary or an instructions manual that is saying us, okay, you have to follow these steps. No, this is not existing nowadays. That's why I think it's important to know how to evaluate your systems, and that's why I present this talk today. So on the one hand, we have to apply quantitative and statistical methods that requires a large-scale experiments. Okay, so we need a large sample of size of participants. And on the other hand, we have to pursue a qualitative approach, focus on case studies and in-depth analysis. So we have a lot of work to do, okay? Because we have to study the quantitative analysis and the qualitative analysis. So regarding these metrics, okay, the point is that metrics are not comparable between bias towards application-specific measures. So depending on the robot, depending on the task, depending on the environment that you are working on, we will have different measures. So what can we evaluate? So we can evaluate the behavior of robots, the ways of interaction. We cannot assume that, for instance, verbal cues will be the best way to communicate with robots. Okay? Maybe for a specific task, we need a contact communication, or maybe a touch screen. Then here we have to consider social and psychological aspects. This is one of the, for me, greatest things on human interaction, that we have to work with different people from other research fields like psychology, medical doctors. We have to work with neuroscientifics, and all together are studying how this interaction has been done. And of course, we can measure as well that these technical characteristics like success rate, interaction times, error rate. Of course, we have to study that, but we cannot avoid human perception. So there are many papers that talk about how robots should work and how this interaction should be measured. I will just talk about two of them. The first one was presented in 2003 by Olsen et al. That he presents some metrics for evaluating the human-robot interaction. So he presents different levels of that measure. The first one was the task effectiveness. It's how well a human-robot team accomplishes some task. Okay? It's something that we can measure. For instance, we can count how many times that team arrives to the goal. Then we have the neglect tolerance, okay? Which is the autonomy of a robot with respect to some task. Sometimes, depending on the task, we don't need to have a robot 100% autonomous. Okay? We need a robot that sometimes the robot is being teleoperated, and other times it's autonomous. So this is the neglect tolerance. Then the robot attention demand. How much a robot is demanding? How many times the robot is asking for help? Okay, this is something that's not bad. I mean, if I have a robot that understands that needs help, okay, the task will resolve easily because we'll ask for that help. Okay, and the found out, which is the number of robots that are working simultaneously at the same time. Then we have the US evaluation metric framework. It was presented in 2009 and presents 4 different items where we can evaluate our system, which are usability, social acceptance, user experience, and social impact. Today, I will just focus on the usability and the social acceptance. And here, for instance, for the usability, we can measure the effectiveness, which is the success rate or task completion rate, the efficiency, which is the rate of speed at which the robot can accurately and successfully assist humans, the learnability, okay, how predictable is capable to do these things as robot, and the flexibility. If we change a little bit the task that the robot has to perform, will the robot be capable of solving the task? Robustness and the utility. And regarding the social acceptance, we have the performance expectancy. Is like the person creates a mental model of how the robot will act or will solve the task. So this expectancy can be regarded from the point of view of performance, effort, and attitudes toward using that technology. So here we are just studying how people are perceiving this interaction. So just as a summary, so metrics and evaluation should be user-centered. Okay, our focus, we just take care of humans, not robots. Okay, we are assuming that the robot is robust, super intelligent, and is performing the task properly. We have to combine qualitative and quantitative measures, and typical scenarios are very important for the community. Like, for instance, if I have a robot working in a hospital, I don't know, taking care of sick people, so I have to make my experimentation there, okay, with that participants. Okay? So now that we know what we want to evaluate, let's see how we present the study design. So I will talk about the research question, the methodology, and the results. And I don't know if I will have time, but here in the first part, I'm assuming that you have a questionnaire, and I will show you how to evaluate your questionnaire and demonstrate your hypothesis. The second part, we talk about how to define and how to create your own questionnaire. Okay? So let's assume that you have a questionnaire, you have some questions, and you want to analyze them. So what is the research question? It's understand how human-robot interaction research questions are constructed. It means we need, depending on the task that we want to solve, we have to define a testable question. So it's crucial to have the wording here. Okay, and here basically what we want is to define what we want to analyze. Okay, and depending on what we want to analyze, we will define the variables, okay, which are the factors, traits, or conditions that can exist in different amount of types in your research study. So if we have the research question, we can define the research hypothesis, which is what I want to demonstrate. Let's see an example in the next slide. I think it's going to be easier to understand. Imagine that I have a robot, okay, and my new hypothesis, that's what I want to reject, is that a more intelligent robot will be equal socially accepted than a less intelligent robot. Okay, so which is the alternative hypothesis? A more intelligent robot will be more acceptable, socially accepted than a less intelligent robot. And here appears the p-value. I guess that everybody knows what a p-value is. Just a comment is the level of statistical significance, and is often associated as a p-value. It has values between 0 and 1. And in human-robot interaction, what we are looking for is to have a p-value lower than 5%. Okay? In that case, we consider we have a statistical significance. So the idea is, if we obtain this p-value, don't worry, because I will show you how to compute this p-value in the further slides. So we have a p-value lower than 0.05, we can reject the null hypothesis, and therefore we can accept the alternative hypothesis. But if we have a p-value larger than 0.05, it doesn't mean that we can accept the null hypothesis. It means that we cannot reject it, okay? So we cannot extract conclusions. Be careful with that, because I saw it in many works that makes this mistake. So what kind of variables do we have? We have the independent variables and the dependent variables. The independent variables are the ones that we can control, okay? We can manipulate for the study, and they are not affected by other variables. On the other hand, we have the dependent variables. Here, the study outcomes and measurements they are the outcome of our study. Okay, let's see an example. Imagine that we have these elderly people that are interacting with these companion robots. So my independent variable is the use or not the use of those robots. Okay, this is my independent variable. And the dependent variable will be the participant's response. Okay, it could be the acceptability of the robot, the times that people interact with the robot. So for each independent variable, I have a group of a studio. So for instance, for the first one, I have a group A, which is the use a pet robot as a companion robot for elderly people, and group B, don't use a pet robot as a companion robot for elderly people. So it has to be mentioned that as more independent variables you have, more groups of people you will have, and the number of participants increases. So be careful with the number of independent variables that you are using. So the research question determines the hypothesis that you want to demonstrate, and those hypotheses determines the study variable that you want to define. So when you want to do your interaction experimentation, you have to analyze what do you want to demonstrate with this experimentation, define the research questions, the hypothesis that you want to demonstrate, and you will have the variables of the study. Okay, so of course, as I said, you have to consider which are the possible dependent variables and which are the independent variables that might be important. So the methodology. Okay, so how do we obtain our data? How do we obtain the data that we need to demonstrate our hypothesis? Here we have three items. We have the procedure, how do we obtain that data? Participants, who will participate, and measurement. What do I want to measure? Regarding the procedure, it's very important when you are doing these experiments to define how your study will be conducted. Okay, and what are the steps of that study? Here I'm showing you a video. This is a robot located in Japan. This robot worked during 5 days in a hospital, interacting with visitors. So here it is necessary to understand what are the instructions to the research give to the participants, what does the robot and when, and how does the robot react to humans. Okay. Of course, we need to know how are the conditions varied and where and when is the study conducted. So here we have to define, in this case, in the example of the video, we define that the robot is working in a hospital, during 5 days, interacting with the people. In that case, we want the robot being proactive, not reactive. It means that the robot approaches the people looking for an interaction and understanding if the people want to interact with it or not. Okay? In case that the people don't want to interact with, the robot just pass by and look for another participant. Regarding participants, this is crucial in your experimentation and remote interaction. Why? Because you have to define who will participate in your study. If you are working with children, you have to make your experimentation, of course, with children, to demonstrate your hypothesis. If you're working with elderly people, your population has to be elderly people. Okay? So choose a sample of people that represent the population, number of people needed to validate. I tell to my students that at least we need 20 or 30 people in our first trial of experimentation, okay? Not less, because if not, we cannot extract conclusions. Okay? And of course, recognize the limitation of your samples. For instance, what happens at university, that most of participants are students in the university. So we have here a sampling bias, okay? Because participants are selected are not representative of the population. Okay, and be aware as well of the response bias, which are shared with volunteers influences a study variable. Okay.
Anaís, you have some questions.
Okay. Peter, you just okay. Yeah, I think it's good to check what Rashid Alami is doing. Okay, in your neural interaction taxonomy, where do you characterize the rehabilitation exoskeleton? Okay, depending on the task, we will use different strategies for that for that classification. For instance, I will move backwards because I think it's going to be easier. I have to move a lot. Sorry for that. Usually, if we pick, you have two options, okay? The first one is the definition of all the items here, like here. So instead of having this robot, you have an exoskeleton, and then you define how is the communication. For instance, it's contact communication in that case. Task of the robot, helping people to move, for instance, the availability of the robot, the proximity. Okay, so you define all these items. Okay, if not, you can also work with that. In exoskeleton, you will say that it's not an industrial robot. We can consider that they are assistive robots, but they are not social assistive robots, okay? Because they do not communicate with people. They do not follow social conventions, for instance. Okay, did I answer your question, Ibrahim? Okay, thank you. So I will move forward. Okay, for that. Okay, and I think I was here, okay, on with participants. So regarding participants, as I said, it's very important the set of people that you choose to perform your first experimentation. And there's something new that appears like 3 or 4 years ago. As robotics, the capacity of the robots and the capability are increasing a lot. And artificial intelligence also is working together with robots. So most institutions have what is called an ethics committee. It means that every time that we want to start a new research, we have to ask permission to that ethics committee. For instance, in UPC, we have one ethics committee. Okay? When we have the validation of that committee, then we can start the experimentation. And what we always need is a participant consent to fulfill by the participants. Here we are giving all the instructions, like which is the PI of the project, I don't know, which is the central affiliation, the place that the study will be carried out, blah, 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 the contact information, okay? And some instructions. Okay? For instance, if we are recording the experiments, we have to ask permission to record their faces and all that stuff. I mean, this is administrative stuff. It's very boring, but we have to do that. Okay, and also we have to give instructions to the participant. Okay, like explain a little bit how the experiments will be developed, how the robot will act, what is the purpose of the experiment, but try to give the minimum information. Okay, not to because if not, we are like conditioning the participants. And finally, the measurement. What we want to measure. So here we can collect two types of data. The first one is the qualitative, and the second one is the quantitative. And ideally, most human interaction studies include both types of measurement. Okay, so we want to use both of them. Okay, because each one gives us a different information that we can extract. So the idea here is that a good measurement is accurate and repeatable. If we experiment with just 5 people, I'm pretty sure that if you have a 6th another person, we won't have the same results. So it will be very different. So we need a large set of people. So regarding the qualitative, okay, how do we obtain these qualitative data? Okay, this non-numerical. We can have special expressions, topics of utterance. So we collect them through observation. So the research has to observe how people are acting, doing interviews or open-end survey questions. So, and here are used to provide quotes, case studies, and code it into quantitative data. The most practical thing that we can do is convert this qualitative data into quantitative data. Okay? And depending on of your questionnaires, you will be able to do that. So let's see some examples of type of questionnaires and questions. The first one is the open-end questionnaire. Here we are giving to the respondent the capacity to have no restriction. Okay, can answer whatever it wants. Like, tell me about your perception of the robot. Why do you think the robot behaves in that way? Do you like the robot accompanying you in a social scenario? Okay. Here, we can allow the respondent to voice their feelings, okay, and give us a lot of information, okay, and can be answered in depth and allow for original, unique, and response. But the difficulty here is how do we analyze these results? Because it's very difficult to analyze this kind of results. Okay, we have a subtype of these kind of questions, are the leading questions. Here, we are just telling the participant how to answer. Okay, for me, this is make tricks. Okay, so don't try to use this kind of questions. Like, what do you think of the horrible effects of pollution? So you are saying that they are horrible, and maybe the participant don't believe the same than I. Okay, and then we have the closed-end questionnaires, which is it's more easy to convert into quantitative data. Okay, for instance, we can use a multiple choice, rating scales, yes or no options. Okay, so here, for instance, let's see an example of the closed-end questionnaire versus the open-end question. So, for instance, in closed-end, we have, would you recommend our robot product service? Yes or not? No? Or, on the other hand, what were the main reasons you choose your robot this behavior? So, depending on what you want to analyze, you will choose one type of questions or not. Okay? Which are the advantages of using this kind of questions? The first one is that it's very expensive. It's cheap, you can use many times that you want. This is practical, it's a good way to gather data. It's a quick way to get results, and it's getting that information from a large audience, so we can really keep talking to it. Regarding comparability, it can be used to compare and contrast on research, and it's easy to analyze and visualize. Okay? And we have the respondent anonymity. This is important because sometimes people act as we expect to act. So if it's anonymous, they are more truthful. And finally, questionnaires can cover every aspect of a topic. Okay? You can ask many questions. But limit, more or less, my recommendation is to use more or less about 10 questions. The idea is that the questionnaires should be answered in 5 minutes, no more than 5 minutes. If not, people get bored and they answer randomly. So, disadvantages of the questionnaire. We can have dishonest answers. Respondent may not be 100% truthful with the answers. You can have answered questions, so make your survey short to get better completion rates. Difference in understanding and interpretation. Users may have different interpretation of your questions or do not understand something. It's hard to convey feelings and emotions. Maybe you don't capture some hidden feelings if you do not observe participant behavior. Some questions are difficult to analyze. Okay, for example, in the open-end questions, when they are completely free to answer, it's very difficult to analyze. And then we have the unconscientious response. There is no way to know if the respondent has really understood the question or read it through before answering. And finally, the questionnaire fatigue. Many questions or many times to fulfill the question. So try to make your the questionnaire short. Okay? So advice to implement your questionnaires. Figure out what information do you want to extract. Keep your questions simple, clear, direct, and short. People don't read. Trust me, don't read. So make your question short. Use words with clear meanings. Use only 1 or 2 answer method like a scale or fill in blanks. Create your questions, it takes 5 minutes or less to complete, and avoid offering too few or too many options. Okay? So this is to collect this qualitative data. Qualitative data is more or less the same. Okay? Here it's more easy to analyze the results. Okay, and we will collect again using surveys. And here we have two kinds of questions. The first one is the semantic differential and the Likert scale. The first one, we have, for example, the color blue makes me feel sad, and you have to choose between one option. And the second one is the color blue makes me feel, and you have like numbers. And this is very easy to convert into quantitative data, and then we can analyze them with choosing a statistical test. Okay, and we have these numerical results. Okay, again, what can go wrong? The social disability bias. People try to act in ways that we are socially acceptable, and the confirmation bias. Researchers with an hypothesis evidence supporting that the hypothesis is more clear. I will skip that because I'm running out of time. I just want to comment that you can create your own questionnaires if you want, but you can use existing ones that are already validated. And here I'm giving you this link. It is the Godspeed survey. That it's a long questionnaire, but you can just use part of it. It's a validated one, and it's very easy to use and to extract information, and you can change a little bit the questions in order to demonstrate your hypothesis. So I will recommend to use this one. So the results, let's see how do we obtain the result, which is the most important part. Okay. I will skip this part because you already know how is the data. It's categorical, ordinal, numerical, you already know that. So I will skip this part as well. And I will focus on here. So as I said, we have an hypothesis that we want to demonstrate. We have the null hypothesis, which is the one that we want to reject. And we have the p-value. Okay, so it's here. The hypothesis that we want to demonstrate. A more intelligent robot will find the fastest way out of the maze, which is the null hypothesis, the one that we want to reject. A more intelligent robot will find the same way out of the maze than a less intelligent robot. Okay? So, which test do we have to use? Okay? Depending on the variables and depending on the nature of the variables, we will use different statistical tests. Okay? I will give you the most typical ones, and I will show you how to use on Python, because I think you will see that it's very, very easy. And using that, I mean, your experimentation will be well demonstrated. Okay? So, ask yourself, do you have a different relationship question? How many independent variables are you testing? What type of data is the independent variable? How many dependent variables are you testing? Usually it's one. And what type of that data is the dependent variable? Okay? Is my data normally distributed? This is very important because there are some tests that it can be only used if your data is normally distributed. So you have to demonstrate that the data is normally distributed. If not, you are making a mistake. So let's see some examples. If your dependent variable is categorical, okay, you can use the chi-square test. Okay? So here, the independent variables, we have independent variables with two or more groups, the dependent variable with categorical data, and test whether the frequencies of observed values is what we expected. Okay, so let's see an example here. I will change my screen. Okay. Are you seeing my code? I guess so.
Yes.
Okay, thank you. So basically, we have to know what to import into Python. Okay, basically, if you want to use this T2 contingency, you have to import this library. And here we have this database that I just created for you. It's like we have the gender, okay, and if it's a smoker or not. Okay, with the t-test, the chi-square example, we create this contingency table. So here we can see that we have 10 women that are not a smoker, 10 men that are non-smoker, and 10 women that are smokers, and 20 men that are not that are smokers. Okay. So we can see it with the percentage as well, or we can normalize this table. Okay, you can see. I will upload this code if you want it, and you can use it if you want it. We can plot the heat map. We can do a lot of things with Python. You may know. Okay? So here, my hypothesis. So if I apply this T2 contingency of my data, see that I have a p-value of 37%. Okay, 37% it's larger than 5%. So it means that we cannot reject the null hypothesis. Okay, The neutral hypothesis was that smokers and gender are independent. Okay? So we cannot reject that. But it doesn't mean that we can accept the null hypothesis. Okay? So with that, we don't have extra information. Okay, we cannot accept that. So this is how we use this chi-square example. I go back to my presentation. Okay, there's a particular case, which is this Magnifies test. Here in that case, we have the independent variables with too much groups. It's commonly used with the pre-post. So you make experiments, you make a survey before the experiment, and then you make the same survey after the experiment. Okay, and we usually have two possible values with a dependent variable, true and false. Okay? You can also use Excel if you want. I don't like it, but you can actually give you an image where you can find all these tests. I recommend to use Python, but do whatever you prefer. Then another example, if our dependent variable is an interval or ratio, okay, we can use a t-test, but be careful because here we need that our data has to be normally distributed. Okay? If not, we cannot use the t-test. And there's a particular case, which is the ANOVA. A lot of people is using this ANOVA. Here we have independent variables with more of two groups, and the dependent variable with normally distributed, and it is a t-test extended to work with more of two groups. Again, you can use Excel if you want to, but I do recommend to use Python. So I will move here. I will show here. Okay. So here I download this database. Okay. Here we have 4 different treatments. Okay, so which are groups for ANOVA. Okay, and treatments are independent variables and termed as a factor. Okay. So here we can see that we have treatments that can have 4 different values, A, B, C, and D, and we have a value. Okay, so this is my data. We can plot using box plot. I want the here. Here, okay. So I'm using here the F1-way ANOVA with the 4 different options, and I'm obtaining a really small p-value. Okay, you can see here. 2.6310 minus 5. So it's a really small value. Okay. So it means that I can reject the null hypothesis, so I can accept the alternative hypothesis. So we can conclude that there are significant difference among treatments. Okay? Let's see the second example here, that I'm adding a new independent variable, okay, which is here. Okay? So we have genotype, year, and a value. Okay. Again, I can do some graph that helps me, and here it's where I'm computing my p-value. Okay. So here we have, if we're just using one variable, which is genotype, if we're just using the variable of year, and if we are using both variables, okay? And for each one, I have this p-value, okay? And as you may see, for all of them, the p-value is lower than 0.05. It means that I can reject the null hypothesis and accept my alternative hypothesis. So we can conclude that type of genotype significance affects the yield outcome. The time also affects the yield outcome. And interaction of both genotype and time significant affects the yield outcome. Okay, so here we demonstrate how to accept our alternative hypothesis. Okay, and the last one is like, as I said, of course, if my data is not normally distributed, then you have to use the Mann-Whitney-Wilkinson test. It's very easy to use as well. It's like the other ones. You just have to download the libraries on Python and go away. But how do we know that my data is normally distributed or not? There are 2 different tests, the Kolmogorov-Smirnov and the Shapiro-Wilk. You can use both of them. And let's see an example of the Kolmogorov-Smirnov to demonstrate if my data is normally distributed or not. There's that one here. Okay, so here, I'm creating a data, okay, following a Poisson distribution. So it's not. We know that it's not normal distributed. So it's so easy. We just import the KS test, okay, and you ask your data. It's normally distributed, and you have a value of 0. So of course, the data is not normally distributed. Okay. We also can compare with that two different set of data and see and check if they are distributed following the same distribution. Like have data 1, which is a random following a normal distribution, and data 2, the log normal. So it's so easy. You have to put keys to some data 1 and data 2, and you see that they have a value of minus very, very small. So we can conclude that both data are not they're not following the same distribution. Okay, let's continue. Just some note, as I said, be careful with the p-value. We always want a p-value of lower than 5%. As more groups of independent variable less significant, it means that you need more and more participants, and the effect size, okay, how different are your groups. So I think I just have 5 minutes. So I will skip that part because it's how do we validate our questionnaires. I think, Victor, I will be able to upload my slides. So I will give you.
Yes.
Okay, so you will check everything and you will have all the information. The point here is that if you are not using a known questionnaire like the Godspeed one that I showed you, you have to demonstrate that your questionnaire is valid. Okay, so here I'm giving you the guidelines that you have to follow to demonstrate that. Okay? I want just to comment something that I think that you may see in different papers. It's something called Cronbach alpha. Cronbach alpha is a value between 0 and 1, and what it's telling us is that if you have, for instance, I want to evaluate the intelligence of the robot, okay, and I have 5 different questions regarding this topic. So this alpha, Cronbach alpha, gives up a value, okay, and it has to be not lower than 0.7. It is lower. It means that there's not that the questions are not following the same strategy. So the idea here is to delete one of the questions. Okay, you have to achieve a value upper 0.7. I think this is very typical to see on papers, and that's what. Okay, so I finished here. I will upload my slides, and you will check the missing part. So thank you very much, and I will be very happy if you make me questions. Monica, can we have access to the notebooks? Of course, I will give all the information to Victor, and Victor, you will be able to upload everything, I guess.
Okay.
Okay.
I will upload the video and also your material.
Okay, thank you very much.
Do we have more questions?
So be careful with the experimentation, and please don't forget humans when you are having humans and robots working together. Thank you very much for coming today.